Hello and welcome to lesson number 10. Today we are going to introduce what a concept that we call discrete probability distributions. Now, before we get into discrete probability distributions, I want to make sure that we can pick apart these three words that define what exactly it is that we're going to do now. First of all, let's start off with discrete. So we learned the difference between discrete and continuous variables. And this was back at the beginning of the semester. And if you remember, discrete variables are variables that you can count on your fingers. So that is, you can draw a one-to-one correspondence with each object in front of you and with your fingers, assuming you had an infinite amount of fingers. It doesn't take on an infinite amount of possibilities, so it's not continuous. And I want to make sure that you're comfortable with what it is that we're talking about when we talk about a discrete variable. Okay, so let's take a look at these two examples over here. Or actually, we have, let's say, 1, 2, 3, 4, 5, 6, 7 examples over here. And let's make sure that we're comfortable with which one of these variables would represent discrete variables and which one would represent continuous. Again, we're going to talk about discrete probability distributions. So it's important that we remember what a discrete variable is. Okay, so the first example, the time it takes a student selected at random to register for the fall semester. Now remember, time is something we need to measure, so it's going to be on a continuous scale. Something that's 5 seconds may not actually be 5 seconds. It could be 5.0062893. We can take on those continuous values, an infinite string of continuous values. So that would be an example of a continuous variable. The next example, the number of, sorry, it should be of, bad checks drawn on upright bank on a day selected at random. So the number of bad checks that are drawn, that's going to be discrete. You can count them. We counted 30 bad checks or 200 bad checks or 199 bad checks or 0 bad checks. So these are all numbers that you could count with your fingers, assuming that you had a lot of fingers. We don't need a scale to measure it. It's something we can count, so that's discrete. Okay, so let's take a look at C and D. The amount of gasoline needed to drive your car 200 miles, the number of traffic fatalities per year in the state of Florida. Well, the amount of gasoline needed to drive your car 200 miles, well, 200, remember when we talk about the amount of gasoline, that's something that we need to measure, right? We need to measure how much it is in terms of gallons. We normally have a pump that will do that for us, right, when we're filling up our car. So that's an example of a continuous variable. If we think about the number of traffic fatalities, so it's saying how many people died. And again, this is something we can count, assuming we have a lot of fingers. 4,389 people died. It's not a continuous scale. We wouldn't say 4,389.2 people died. Why would that make sense that 0.2 people died? So this is an example of a discrete random variable. Take a look at E, F, and G. Pause it right now, take a look at these three and see if you can figure out if these guys represent continuous or discrete random variables. Okay, so take a look at E. The distance a golf ball travels after being hit with a driver. Well, remember, distance is something that we have to measure. So that's going to be continuous. We need a tape measure, we need a ruler, we need something to help us measure distance, a counter, some type of counter to help us measure distance. The number of ships in Pearl Harbor on any given day. Well, again, that's something we can count with our fingers, right? So that's discrete. Your weight before breakfast each morning, that's something we need to measure. We're not actually 123 pounds. We're probably 123.064289, right? It's on that continuous scale pounds. So this is continuous. So now that we're comfortable with discrete variables, right? And again, they're variables that you can count on your fingers. Let's talk about what a discrete distribution is. All right. And then we're going to talk about how we can assign probabilities to these guys as well. So a discrete distribution is a probability distribution where the sample space is countable, right? And remember, countable means discrete. We can count it. The random variable in such a case can only take point values. For example, number of people or number of coins, etc. So again, what we're doing here is we're saying that these are points on a number line. They're not continuous values. These are points on a number line. So again, we can count them, countable. Now let's talk about the conditions for a discrete probability distribution. If we're looking at a discrete probability distribution, we have a couple of conditions here. First of all, when we add up all of the probabilities, we should get 1. What that means is we're covering the entire sample space. We're covering the entire range of the sample space. So one thing that we need to check for is that when we sum up the probabilities, in order for it to truly represent a discrete probability distribution, when we add up all the probabilities, we should get 100% or 1. Okay, something else that we have to check for, remember, is that probabilities have to be between 0 and 1. 0, P of X, and 1. Probabilities have to be between 0 and 1. Okay, so for discrete, and the last thing we have to do as well is we just have to check and make sure, and it's in the definition, but I'm gonna put this in here just to make sure that you're comfortable with it. We also have to check and make sure that the variable we're dealing with is discrete. Okay, so we really have 3, let's call this 3 conditions that need to be satisfied in order for something to represent a discrete probability distribution. Okay, Professor Hirsch, what is this thing that we're talking about? What is a discrete probability distribution? Well, let's take a look at some examples. Now, we're just going to look at some examples, and then we're going to talk about how we can find the mean, the standard deviation, and the variance of discrete probability distributions. But first, I just want you to look at them and really to be able to understand what's going on. So let's take a look at the first example. Do the following represent a discrete probability distribution? During skiing season, there are numerous accidents. According to Lindy Gomez, the following represents the number of accidents per any Monday and the corresponding probabilities. Okay, so first of all, let's talk about what X represents, and let's talk about what P of X represents. X represents accidents. How many accidents there are, and remember, we're looking at Mondays. How many accidents there are on a Monday? So 0 accidents on a Monday, 1 accident on a Monday, 2 accidents on a Monday, 3 accidents on a Monday, 4 accidents on a Monday, 5, 6, and 7. That's what each one of those represent. Now, P of X represents the probability that you have that total number of accidents on a Monday. So for example, if I were to say to you, what's the probability that we're going to have 2 accidents on a Monday, right? So you say, okay, well, X represents the number of accidents, that's 2. And the probability we're going to have 2 accidents on a Monday is 28%. What's the probability we're going to have 6 accidents on a Monday? Well, the probability we're going to have 6 accidents on a Monday is 0.011 or 1%. Now, why do we create these probability distributions? Well, for a few different reasons. One of the reasons that we create these probability distributions is, let's say that you work as you are Lindy Gomez, and you have to figure out how many doctors or how many nurses you should have on staff on Mondays at your skiing at your ski slope, right? So you look at this and say, well, you know, looking on my Mondays at the discrete probability distribution, it looks like the highest probability that we have here is that we're going to have 1 accident. So I don't need to staff this with a lot of people, with a lot of doctors or a lot of nurses, because I'm probably going to have, according to this distribution, 1 accident. Is it possible we have more? Sure, it is possible, but the highest probability in here is that 1 day. Now, if you look at the discrete probability distribution for another day of the week, let's say we're looking at Saturday or Sunday, Then, because ski slopes tend to get a lot more crowded on the weekend, right? That's when people aren't working. Then we would reconfigure this and say, oh, it looks like maybe, and again, I'm just conjecturing here, maybe there's going to be a higher probability for 6 or 7 accidents because there's a lot more people there and more people are crashing into each other and hurting each other. In that case, then we want to hire more doctors to come in on the weekend, right? Then on a Monday. So one way we can use discrete probability distributions is to our advantage, just as the example that I just talked about. Now, another way that we can use discrete probability distributions is to figure out what the mean or the expected value is. And we're going to talk about that in a second. But I just want to answer this question. And the question is, do the following represent a discrete probability distribution? Now, remember, we have to check 3 things. First of all, first thing that we want to check for, is our variable discrete? Is our variable discrete? Well, are the number of accidents discrete? Sure, because you can count them on your fingers. We had 10 accidents, we had 2 accidents, we had 1 accident, we had 0 accidents, whatever it is. So yes, the variable is discrete. Now we want to check and make sure that each variable has an associated probability that's between 0 and 1. So let's check and make sure that each variable has an associated probability that's between 0 and 1. Well, okay, 0.04. And remember, between 0 and 1, you're thinking about between 0 cents and $1. So this is all the change between 0 and 1. 0.04 is between 0 and 1. 0.492 is between 0 and 1. 0.28 is between 0 and 1. 0.091 is between 0 and 1. 0.054 is between 0 and 1. 0.031. 0.011. And this 0.0, that little plus over there, means it's a number that's really close to 0, but it actually is a number. We're just saying it's not exactly 0, but it's really close to 0. It's the same thing as saying the probability that you flip a coin and it lands on its side. Well, the probability of that happening is kind of, it's not 0 because it is possible to happen, but we kind of ignore it. So it would be the same thing here. It's a number that's close to 0, but it's not exactly 0. So we checked and made sure that each one of the associated probabilities is between 0 and 1. And now the last thing we have to do is we have to check and make sure that all of the probabilities sum up to 1. So that is, when I add all of the values in my probability column together, do we get 1? So let's check. I'm going to do this on my calculator. You do it with me. 0.04 plus 0.492 plus 0.28 plus 0.091 plus 0.054 plus 0.031 plus 0.011. And actually, when we add these up, I get 0.999. Now, 0.999 isn't exactly 1, but remember, there's going to be a little bit of rounding here. So it's possible for us to be over a little bit of 1, and it's possible for us to be under a little bit of 1. But assuming that we're not exactly equal to 1, if there's rounding errors in there, like 0.999, a little bit under 1, or 1.01, a little bit over 1, then that's okay. We just kind of ignore it and say, okay, there were some rounding differences. It's close enough to 1, so the sum of these values do equal 1. I'm just going to double check real quick over here. 0.04 plus 0.492 plus 0.28 plus 0.091 plus 0.054 plus 0.031 plus 0.011. And the same thing, I get 0.999. So answering the question, does this represent a discrete probability distribution? The answer is yes, and this should be does. The answer is yes, it does. All 3 of these are met. The variable is discrete. The probabilities are between 0 and 1, and the sum of the probabilities are equal to 1. So let's take a look at another example. Does the following represent a discrete probability distribution? Let X represent the litter size of a female golden retriever, and let P of X represent the probability she is a litter of that size. Okay, so X is the number of puppies that the golden retriever is having, and P of X is the probability that the golden retriever will have that total number of puppies. So just kind of looking at this, if I were to say to you, what is the probability that a golden retriever will have exactly 6 puppies? Then you say, oh, there's a 67% chance. Or what's the probability that a golden retriever will have 3 puppies? Well, there's an 8% chance. Now, and you get the general idea here, right? So X represents the number of puppies. P of X over here represents the probability she's having that total number of puppies. Okay, so let's check and make sure that all 3 conditions work in this example. Does this represent a discrete probability distribution? So again, first of all, is the variable discrete? Is the number of puppies that a golden retriever has discrete? And the answer is yes, you can count the number of puppies on your hand. Second of all, is each probability between 1 and 0? So for each associated discrete value, we have to make sure the probability is between 1 and 0. So 3 puppies, 8%, right? Or 0.08 is between 1 and 0. 0.112 is between 1 and 0. Between 1 and 0. Between 1 and 0. Between 1 and 0. So each probability is between 1 and 0. So that checks. Last but not least, now we have to check and make sure that the sum of the probabilities is 1. That means the entire sample space is covered. So let's see what's going on here. We have 0.08 plus 0.112 plus 0.242 plus 0.67 plus 0.80. Oh no, look at this. What do we get? We get 1.904. So when we say, is it true that the sum of these probabilities is equal to 1? No, this is way above 1, right? If you were to think about this in terms of a percent, that would be 190%. And you want to stay somewhere close to 100%, so 99% or 101%. So this is not true. The sum of the probabilities is not equal to 1. So answering the question, does it represent a discrete probability distribution? The answer to that is a resounding no. So now that we're comfortable with how to look at a discrete variable, how to look at their associated probabilities, and how to determine if it actually does represent a discrete probability distribution, we're going to talk about how to find the mean, the variance, and the standard deviation of a discrete probability distribution. Okay, let's start off with the example of the mean. For any discrete probability distribution, to find the mean, it is the same thing as saying, remember this little symbol over here means the sum of X times P of X. Okay, so the mean for any discrete probability distribution is represented by the formula, the sum of X times P of X. Well, what does that mean? Remember that X represents your variable, whatever it is, and P of X represents the probability that variable occurs. So you just multiply these two together, right? That's X times P of X, and then add them up. And that will tell you what the mean or what the expected value is. Now we'll talk about expected value in a second. So we also have formulas for standard deviation. The formula for standard deviation, which is this guy over here, is the square root of, right? We're familiar with that square root of because we use that for standard deviations back at the beginning of the semester when we were talking about finding the standard deviation of a data set, not of a discrete probability distribution, but of a data set, times the sum of X minus mu quantity squared times P of X. Okay, so what does that mean? Okay, well, that means first we have to figure out what the mean is. Then we're going to subtract each variable from the mean and square that. Then we're going to multiply those by their associated probabilities. And then we're going to add them up. And then we're going to take the square root of it. So it's similar to where we didn't have the P of X. Instead, we had divided by N when we were talking about finding the standard deviation of a data set. It's similar to that, right? The structure is a little similar to that. Instead of dividing by N, we're multiplying each one of these by the probability that that variable occurs. Now, remember that the variance, which is the same thing as saying standard deviation squared, is the standard deviation, but without taking the square root. So it's just that value that's under the standard deviation without taking the square root. Okay, now that we talked about the formulas, let's do one or two examples. But before we get to the example, I want to make sure that you understand when we talk about the expected value of a probability distribution, that's the same thing as saying the mean. So when we're looking at it, that is, we look at the probability distribution, and so let's take a look over here. When we look at the probability distribution over here, right, we would look at this and say to ourselves, how many accidents would we expect on a Monday based on this probability distribution? If this was a probability distribution over here, we would say to ourselves, how many puppies would we expect based on these probabilities? So oftentimes, instead of saying what is the mean, oftentimes we'll hear the expected value, the expectation, the mathematical expectation, or the mean. All of those have the same type of meaning. So the mean is the same thing as saying expected value, which is the same thing as saying, excuse me, which is the same thing as saying the expectation or the mathematical expectation. Okay, so let's take a look at an example. Let's consider the following discrete probability distribution below, where X represents the number of cars per household in New York, and P of X represents the probability a family has that number of cars in their household. Now, remember, the first thing that we always want to do when we're taking a look at this is we want to check and make sure that this does represent a discrete probability distribution. So how can we tell? Well, first of all, I hope you're comfortable with the fact that our X value, the number of cars, is a discrete variable, right? You can count on your fingers how many cars somebody has. Now, each one of these probabilities is a number between 0 and 1. And if we sum up these probabilities, and do it with me, let's sum up these probabilities. We get 0.03 plus 0.13 plus 0.70 plus 0.10 plus 0.04. We get, hold on one second, let me try that one more time. 0.03 plus 0.13 plus 0.70 plus 0.10 plus 0.04. We get a total of 1. When we add these up, when we sum up these probabilities, we get a total of 1. So the idea is, well, let's start off, and so, okay, all right, sorry, let me take one step back. So this does represent a discrete probability distribution. Now, the next thing we want to figure out here is we want to find what mean is, what the mean of this probability distribution is, or what's the expected value. So that is, real quickly, if you were to take a look at this, if you were to knock on the door in the average household in New York, how many cars would you expect them to have? Well, if we take a look, the highest probability here is 2. Right? Do you guys see that? The highest probability is a 70% chance they'll have 2, but then there's a 13% chance they'll have 1 and only a 10% chance they'll have 3. So it looks like something a little bit under 2. So we would say, right, it's something that's kind of leaning a little bit heavier, a little bit under 2. So we would say the expected number of cars, just kind of looking at this probability distribution, I'm going to conjecture or think that my mean is going to be something close to 2, maybe a little bit underneath it. Well, how do we figure out exactly what it is? Well, here's how we do it. First of all, I'm going to take this probability distribution, and I'm just going to right next to it X times P of X. Because remember, the formula for the mean is the same thing as saying the sum of X times P of X. Okay, so what does that mean? Well, the first thing I'm going to do is I'm going to multiply each X value by my P of X value. Okay, well, 0 times 0.03 is 0. 1 times 0.13 is 0.13. 2 times 0.70 should be 1.4. 3 times 0.10 is 0.3. And then 4 plus, so this means 4 or more. So maybe 5, 6, 7, 8, 9, whatever, you know, some people have hundreds of cars. 4 times 0.04 is 0.16. Okay, and let's see what we get when we sum up these values, right? So here's our X times P of X. Multiply each random variable by each probability. And now let's add these guys up. So what happens when we sum up this column? Well, we get 0 plus 0.13 plus 1.4 plus 0.3 plus 0.16. And look at what we get. We get the sum of these values is equal to 1.99. So what this means is you would expect, based on this probability distribution, the average person in New York will have 2 cars. The average household, sorry, the average household in New York will have 2 cars. So that would be our expectation for it. And that's also the same thing as saying the mean. So the mean is 1.99. So the mean's the easy part. Now here comes the more interesting part. I don't want to say it's complicated, just say it's a little more interesting, because we just have a little bit more work that we have to do when we're finding the standard deviation. So I'm going to start off with, and let's go back up here to the formula for standard deviation. Sum of x minus mu. Okay, so what that means is we're going to take a look over here. First of all, we know what mu is, right? Mu is 1.99. That's what we just figured out over here. We figured out the mean is 1.99. Now I'm going to create a chart, right, for this standard deviation. It's going to be a big chart. Follow along with me, please. It's going to be a big chart. Okay, over here, we're going to list the x's. Over here, we're going to list x minus mu. Over here, we're going to list x minus mu squared. Over here, right, so here's what we're doing. Take a look. We have x minus mu squared, and then the third column is going to be x minus mu squared times p of x. I'm sorry, the fourth column. Okay, first of all, I'm going to put in my x's, which represent the number of cars. I have 1, 2, 3, 4, 5, so I'm going to do probability of family of 0 cars, 1 car, 2 car, 3 cars, 4 plus cars. Okay, so x minus mu. Okay, so remember x over here is 0. Mu is 1.99. I'm going to do the same thing, 1 minus 1.99, 2 minus 1.99, 3 minus 1.99, and then 4 minus 1.99. So when you're using a discrete probability distribution, the first thing that you have to do is you have to figure out what mu is. It's the same thing with when we're finding the standard deviation. It's the same thing that we did before, again, when we were finding the standard deviation of a data set. 1 minus 1.99. 2 minus 1.99. 3 minus 1.99. And then 4 minus 1.99. And again, pointing out to the similarities, or just pointing out the similarities between standard deviation of discrete probability distributions and regular standard deviations. So if a household has 0 cars, this is 1.99 units below the standard, below the mean, right? Because remember, the mean is about 2 cars, or 1.99 cars. If somebody has 1 car, that's 1 car less, right, or negative 0.99, which is very close to -1, than the expected value. Okay, 2 minus 1.01 says almost exactly is the expected value, right? 1.99 is very close to 2. This is 1 more car than the expected value, and this is 2 more cars than the expected value. All right, so the next thing we're going to do is we're going to square it. Remember, the squaring makes it positive. So let's square each one of these values. So negative 1.99 squared. And we get this. And now remember, all of these values will be positive in this column. They will be positive in this column because you're squaring the values. A negative times a negative is positive. A positive times a positive is positive. Even if your calculator tells you it's negative, it's because you didn't put the parentheses in correctly. So make sure this column is always positive. I have 3.9601 for that first one. Let's do negative 0.99 squared. You get 0.9801. Let's do 0.01 squared. And we get 0.0001. Let's do 1.01 squared. And then let's do 2.01 squared. Okay, now this last column is we're going to take whatever we have in this column, right, x minus mu squared, and now multiply it by their indicated probability. So we're going to multiply it by this guy over here, this p of x over here. So, okay, so the probability we have zero cars is 0.03. So I'm going to multiply 3.9601, whatever we get in this column, by the probability, which is 0.03, and then record what we get over here. So 3.9601, oops, 3.9601 times 0.03 gives us, oh, let me erase this guy because we're going to get some crazy decimals going on here. Let's extend u for the long decimals. We will extend u, extend u, extend u. Okay, cap it off over here. So we get 0.118803. Okay, the next one, x minus mu squared times p of x. So we already know x minus mu squared over here is 0.9801. P of x, so the probability that a household has one car is 0.13. Okay, so 0.9801 times 0.13. And there we get 0.127413. Okay, same thing. X minus mu squared here is 0.0001 times p of x. So the probability that a household has two cars is 0.70. And we get 0.00007. All right, let's finish this up. Again, x minus mu squared over here is 1.0201. Multiply that by p of x. So this is for 3 cars, right? And the probability that a household has 3 cars is 10%, so 0.10. Let's multiply these two together. So 1.0201 times 0.10, and we get 0.10201. Okay, one more. X minus mu squared is 4.0401 times p of x. So this was for 4 cars, right? 4 or more cars. So the probability we have 4 or more cars is 4%. And when we multiply those two together, 4.0401 times 0.04, and we get 0.161604. Okay, so what was the whole point behind doing that? Well, if we go back up here and look at the formula for standard deviation, look at this guy over here, right? It's x minus mu squared times p of x, which we just did. That's that last column, right? This is the x, sorry, I'm going down here. This is the x minus mu squared times p of x. What do we do with those values? Well, we sum them up. Okay, so we did x minus mu squared times p of x. Now we're going to sum them up. So we're going to add up this last column. Sum of these variables over here, the sum of this column, x minus mu squared times p of x. Let's see what we get. So we're going to add up 0.118803 with 0.127413 with 0.00007 with 0.10201 with 0.161604. And when we add them up, we get 0.5099. Okay, so the sum of those values are 0.5099. Let me just write down the formula here one more time. So the standard deviation is the square root of the sum of x minus mu quantity squared times p of x. Okay, so we did x minus mu, right over here. We did x minus mu quantity squared right over here. And then we did x minus mu quantity squared times p of x right over here. And then we added them up. So the last thing that we need to do, you see that little square root, is we have to take the square root of it. So the standard deviation is the square root of 0.5099. Now remember, the definition of the variance is whatever's in the standard deviation before you take the square root. So the variance is 0.5099. Again, same thing that we already did when we were looking at the standard deviation of, the standard deviation of a data set. So the variance is 0.5099. Okay, so the standard deviation is what we get when we're done taking the square root of it. So the square root of 0.5099, and we get the standard deviation is equal to, I'm going to round my answer to 3 decimal places, 0.714. Okay, so answering the question over here, answering the questions, which were find the mean is 1.99. That's the expected value, which is to find the standard deviation, which is 0.714. And then to find the variance, remember variance is standard deviation squared, which is 0.5099. Here are your 3 answers to it. Well, okay, so we talked about why the mean is important, right? Why the expected value is important. Well, let's talk about why the standard deviation is important. In terms of outliers, the standard deviation of a discrete data distribution, of a discrete probability distribution, we can find outliers by using the general rule of thumb that anything is an outlier that is more than 2 or less than 2 standard deviations from the mean. Okay, well, what does that mean? That means if you know what the mean of a data set is, and if you add the standard deviation onto it twice, and then if you know what the mean of a data set is, and if you subtract the standard deviation from that twice, that will give you a range of all of the values that are considered to be normal. Anything outside of that range are possible outliers. So let's take a look at this and figure out what the possible outliers for this data set are. Well, the mean is 1.99. So let's add the standard deviation to it 2 times. And this is any distribution, any discrete probability distribution. The rule of thumb is within 2 standard deviations. So that's fixed. And we get 3.418. And then we're going to take the standard, we're going to take the mean and then subtract 2 standard deviations from it. So minus 0.714 minus 0.714. And we get 0.562. So what this tells us is the range of normal values is between 0.562 and 3.418. Well, what does that mean? First of all, remember the variable that we're looking at is discrete. And the variable, particularly in this example, the variable is represented by cars. So you can't have half a car, you can't have 3.418 cars. But what you can say is you can say, if you look at a New York City household, the probability is that people are going to have between 0 and let's round that up to 4 cars. Okay, anything with more than 4 cars, anything with less than 0 cars, so it doesn't make sense on that side, right? It wouldn't make sense for you to have negative cars. But anything more, any household with more than 4 cars, that's an outlier. And then you just ask questions about it. It's a red flag. Why do you have more than 4 cars? Are you really a resident of New York? Right? Because if you're a resident of New York, it's expected that you have between 0 and 4 cars. So this is just a way for us to flag some data, for us to ask some questions about the data. But here, remember, because these are discrete variables, we really want to try to make some sense out of them. It doesn't make sense to have half a car. We can round that down. Same thing. It doesn't make sense for us to have 3.4 cars, so we can round that up. So an outlier, the outliers would be any family that claims that they're a resident of New York that would have more than 4 cars. There's a question or there's something that's going on. Okay, so let's kind of recap everything that we just talked about. We'll make sure you're comfortable with this. We talked about what a discrete variable is. We reviewed what a discrete variable is. We talked about the 3 conditions to a discrete probability distribution. We talked about what x is and what p of x is, right? One of these are the variable, one of these are the probability associated with that variable. We talked about, again, the 3 conditions. And then we talked about how to find the mean of a discrete probability distribution, the standard deviation of a discrete probability distribution, and the variance of a discrete probability distribution. And then we talked about why standard deviation is important, how we can use this idea behind standard deviation to help us find outliers. So that is it for discrete probability distributions, and I will see you next class.